Hello and welcome to the last part of module 6. Here we are going to discuss about entropy, and I have listed the section numbers in the book that we are going to follow for this topic. We want to go in this sequence. There's a reason why I want to start with section 7-6 and then go from 2 through 9 and then 12, 13, and we are going to see all the concepts involved with entropy. So we'll begin our discussion of entropy with the concept of molecular disorder. I want to talk about disorder, and I want you to think about the solid state, a liquid, and a gas. Now, if you think of these three states of matter, you do know that a solid is composed of atoms that are arranged in nice regular patterns. Okay, you know this. And a liquid is composed of molecules that are free to move around, except they do have kind of a tagging force to each other so that they form an interface and they stay within the interface. They pull on each other and they form a liquid surface. Okay, and then a gas, the force between the molecules is very small, so that they don't really try to hold on to each other. They move around more freely and occupy the entire volume, and we call this a gaseous state. If you think of disorder, or if you think of the opposite concept of order, I'll ask you the question: how many numbers are required to describe the state of the molecules? How many numbers do you need to describe this picture of the state of the molecules? And you can describe the state of the molecules that constitute of what could be a solid, liquid, or a gas. You need to if let's say you have n molecules. Each molecule has a position and each molecule has a velocity. That's 3 numbers. That is 3 components and 3 components. So really you need to know, or you need to specify 6n numbers to completely specify the state of a substance, which could be solid, liquid, or gas. Solid, liquid, or gas. Okay. Now, if it is a solid, and let's say they are all arranged in a nice regular repeating pattern such that the distance between them is, let's say, delta in either direction. I told you that 6n numbers are required, but out of 6n, to describe positions, you don't need to know all the 6n numbers independently. If I say that the starting position is, let's say, 0, 0, you can quickly write what are all the positions of the next atoms, like delta, 0, 2 delta, 0, 0, delta, 0, 2 delta, and so on. So what you really need to know is the position of the first atom, that is, say, 3 numbers, plus the lattice spacing. You don't need to know all the numbers, all the 6n numbers. You just need to know 4 numbers for a very simple situation. Now, it may not, the idea is not that you can describe every solid with just 4 numbers. But the idea is fewer than 6n numbers may be enough to describe a solid. There are different types of solids like face-centered cubic, body-centered cubic, hexagonal, There are many types of solids, but if you don't need to know all the 6n numbers to describe a solid. You just need to know fewer numbers than that. Or in other words, you could say that a solid is orderly and it is less complex than a liquid or gas. Now, we didn't talk about a liquid or gas yet. If you take a liquid, I told you that they form an interface and they have molecular forces between them. They freely move around within the liquid, but yet they also exert forces on each other. That is, you can specify out of the 6n numbers, most molecules can have independent positions and velocities. But they must obey some global constraints relation to their interface and intermolecular forces. So in terms of orderliness, a liquid is less ordered than a solid, or I'll just say a liquid is more disordered than a solid. Okay. If you take this argument to the next step, a gas in which there is very less force between the molecules are more free to move. They can occupy the entire volume of the container, more free to move, lesser intermolecular forces, and by this argument you would actually need to know almost all 6n numbers are required to specify the state of the gas. So you can see the argument going that a gas is more disordered than a liquid, which is more disordered than a solid. So we saw that a gas is more disordered than a liquid, which is in turn more disordered than a solid, or on a scale of order instead of disorder, you can think the solid is the most ordered state, followed by the liquid, and then followed by the gas, which is the least ordered state. Now, you are talking about order, right? We are talking about order, okay? Or we need a measure for order. Okay, we need a measure for order, and this is what we define. This is where we define entropy. We define entropy, which is a quantity that can be viewed as a measure of molecular disorder molecular disorder or molecular randomness. We define entropy as a quantity that is a measure of the molecular disorder or randomness. So how do you quantify this disorder? How to quantify disorder? Now I told you my example about the solid state requiring, let's say requiring less than or much less than 6n numbers to describe it completely. A liquid state will require something that's less than 6n, but it's still not as less as the solid state. Okay, and the gaseous state will require nearly 6n numbers to be completely specified. Or in other words, a more disordered state requires more number of descriptive parameters. That is, let's say, the positions and velocities of the molecules. Okay. So if I have a picture, I'm not going to say whether it's going to be a solid, liquid, or a gas. All I have is a bunch of molecules that are moving around. It could be a solid, it could be liquid. Don't worry about what it is. I specify 6n numbers. Okay, of those 3n positions XYZ for each position vector, and then 3n velocities, that is u, v, w components for each velocity vector. Now these 6n numbers can take a lot of possible combinations. They can take a lot of possible combinations. Of these combinations, not all of them are unique. Okay, some of them, like for example, if you have a solid, you have this. Okay, every particle might get the same velocity, or every particle might have similar positions or positions that depend on a fewer numbers. So in this case, it's not always that you need all the possible combinations of the states of these 6n numbers. So let's just think of, if you think of W unique states of a system, which could be a solid, liquid, or a gas. Okay, the entropy is defined as the measure of the measure of the number of possible states. Now, if you have a very ordered systems, W is smaller, implies more order, and a large value of W implies less order. Okay, so the definition of entropy that is commonly used is called K ln W. Okay, entropy is defined as K ln. K is called the Boltzmann constant, named after the scientist Boltzmann who came up with this definition. And W is the number of microstates which are defined by the velocity and position of the constituents. Position and velocity of the constituents. Now, K has units of joule per Kelvin. Okay, I'll write KB. Okay, so entropy itself has units of joule per Kelvin. Joule per Kelvin, and we define the specific entropy, which is joule per Kelvin per kg. This is the extensive version, and this is the intensive version. Okay, so we talk of entropy as K ln W. Okay, and if W is really large, that implies large entropy, and vice versa. Now you can think of solid, liquid, and gas. And suppose you start with the gas, you reduce the temperature. What do you get as you cool down a gas? When you reach the freezing point, you have when you reach the boiling point, you have a liquid, and from that point on, if you continue cooling, you reach the freezing point, you reach a freezing point, and then you have a solid. What happens if you continue freezing a solid? Continue freezing or continue cooling down a solid. The molecules that make up the molecules are atoms that make up that solid. They vibrate less and less about their fixed positions. Okay, as the cooling continues, their vibration, that is, let's say they jiggle around in their fixed positions a little bit, this amplitude reduces as you continue cooling. As you reach the lowest possible temperature, at which all molecular motion ceases. Okay, all molecular motion ceases or stops. We'll define this temperature as absolute zero. Okay, at this temperature, all molecular motion stops, which means if you think of your solid, here is all the atoms, they are not moving, which means their velocities are all zero, and their positions are all frozen solid, which means if you know one of them, you can just say all of them, because you know their spacing. You just need one number, which means the possible number of microstates suddenly reduces to 1, and the entropy that we defined previously, which is K ln W, is K ln 1 or 0. That is, we define the perfect crystal as that with an entropy or minimum with an entropy of 0 and no disorder. At this state, we define the temperature to be 0 Kelvin, or in other words, 0 Kelvin is an ideal temperature. Ideal means it doesn't exist in reality. Ideal temperature at which entropy is 0. We define this formally as the third law of thermodynamics, that states that the entropy of a pure crystalline substance at absolute 0 temperature is 0. This is the third law of thermodynamics, and all entropies measured relative to 0 Kelvin is called absolute entropy. Absolute entropy. So you can think of the entropy scale, which again is a scale of disorder. You have your 0 Kelvin, or the pure or the perfectly crystalline solid in which all motion has ceased, and all temperatures greater than that, and for all states that are to the left of that, we have solid, liquid, gas. Entropy generally increases. The way we increase temperature practically is by supplying heat. So you supply heat that generally leads to an increase in temperature, and to decrease the temperature, we remove heat or extract heat. Okay, so we can supply heat or extract heat. We can also do work, extract work that can also change the heat content through the first law that we have seen before, Q minus W equals delta U. And this is also a way to manipulate the temperature, and that is directly related to the entropy. I just said related, it's not exactly the same. Entropy is a different quantity than temperature. Okay, so we'll see about what is the definition of entropy, or what is the mathematical definition of entropy, and how to use this in the problem in the next video.